was also late come to the campus lah. Um, so we have here 11 students. Okay, we are supposedly to have 39, 15 plus 15 plus how many? About 19 students now. Okay, so that is okay. Today's session, since it is online, I will record it lah. Okay, right. So I'll record the screen. Okay. So I'll start the recording now, and then we'll start our class now. Okay. Start recording. Record here. Okay. All right. Started recorded already. Okay. Okay. For those who didn't come, then can refer back to my slides lah. My recording lah. Just that must remind them to watch it, because if you didn't watch the following lecture you cannot follow, because all the knowledge and concept they are interrelated. Okay, so if you skip one class, then the next class you won't be able to follow until you can catch up back now. Okay, right. So it's here. Okay, okay. Let me see. Okay. 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 All right. So if you can see my slides, then I'll start now. Okay. Okay. So the other day we talked about the solution for this and this lah. Okay. For question A, we say it cannot be expanded in Fourier series DTFS. It is we see that it is cosine, okay, and we see that it is discrete time signal, okay, but it cannot be expanded in DTFS, and uh, their Fourier coefficients cannot be found, okay, because it is not periodic, right? Okay, so we cannot do it, okay, because the equations for DTFS it involve n, right, the fundamental period. So if the signal is not periodic, n cannot be found, and the equation cannot be used, right? But for the second equations, we know that xn equals to this is the first equations for DTFS lah. Okay, summations of ck, right? Ck exponential, right? Positive. Ck exponential j 2 pi kn divided by n, right? So by using comparison method, okay, this cosine, this is a cosine, right? Pi n over 3. It can be using the trigonometry identity, not identity, trigonometry equations. Okay, it can be uh, changed into two exponential terms. All right, so then we compare the exponential term here and the exponential term here for the coefficients, right? So both sides have exponential, they are equals. So we can use the comparison method to find the exponentials, these Fourier coefficients, the constant that associated to these exponentials, right? Of course, you have to make uh, the exponentials angle here, okay, the phase here, the values here, okay, to be similar lah, so that you can see, okay, it actually belongs to which Fourier coefficients, okay. Okay, so we have discussed about this. And you might ask, okay, so if I do not want to use this method, okay, I want to use uh, this method to find my CK, is it okay? Yeah, it would be okay. Just that it is a bit complex, okay. You know that this is a cosine, okay. This would be a cosine uh, pi n over 3. And you found that cosine multiply exponential is difficult to do. So you also will be decided to change this into two exponential, right? And then you have another exponential here. So you have a multiplication of exponentials, right? And then after that, you have two variables to expand it, right? First, you have to expand it over n. Okay, so there will be n inside here, right? It'll be also there's also k inside here, right? So you have to iterate n and iterate the k, right? So in order to find C1, C2, C3, C0, how many, depending on what is the n values. So if n equals to, how many n is there? 6, right? Right, 6, right? So you need to find from 0, 1, 2, 3, 4, and 5. So you have to iterate k from 0 to 5, and then the n also from 0 to 5. Okay, right? Then you can get all the ck lah, but you will get most of them is 0 lah. Okay, but it can be done. Just that there's a little bit complexity here for the multiplication of two exponential. Okay, but uh, we expect to find similar answer lah. Okay, right. So there's two equations here. Okay, can be used. Okay, right. Okay, so we have know how to do this. Okay, let's look at the solution for xn equals to 1100, and it is periodic. Okay, so meaning that it is repeating, right? Periodic. Okay, and the n is 4. Okay, so with n, discrete time signal, okay, then we can use um, the equations of DTFS to find what is the CK lah, to find the Fourier coefficients lah. Okay, and for this round, okay, the equation that we're going to use is the second one, right? We use the second one. So for B, we use the second equations. Okay, so for this one, we use the first equation. So we get to use all the equations to find the CK lah, right? So in this case, right? Let me see, because I wish to look at your uh, Google chat here. Okay, in case you type something that I can directly respond. Okay, but when I play this, then okay, 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 let's do this. Okay. Okay. Okay, so this B is already done. So we are looking for the solution of C. Okay. Directly come to these equations. So we are going to use the equations CK equals to 1 over N summation N equals 0 until N minus 1 for the Xn multiplied with exponential minus J 2 pi Kn over N. All right. So we are looking for CK, and we know that this Xn is 1100, right? This is the origin. Okay. Okay, so first of all, we replace the n equals to 4 into the equations at here and also at here. All right, so we have the equation from n equals 0 until 3 lah. Okay, because 3 minus 1, 4 minus 1 is 3. And here there's a 4, right? There's a 4. Yeah, this is the n. And then here also we change to 4, right? So we have here. Okay. So, and then we uh, we expand the summation, okay, for n starting from 0 until 3. Okay, so you might ask, okay, in this case, if I don't want to choose n from 0 to 3, I mean, I do not want to use n from 0 to 3. I somehow have a feeling that the signal is symmetry. Okay, I want to use uh, -1 to 2. Can I do that? The answer is yes. Okay, because if you see, uh, so this is given, right? So it looks like this. So this is 0, 1, 2, 3. This is 1, 1, and 0, 0 lah. Okay. So uh, so let's say okay, so it's given here, right? So n from 0 to 3 is here. Okay, 0 to 3. So if you want to choose other range, like you want to start from -1 until 2, it's also okay, right? If you want to start from -2, okay, until 1 is also okay. So depending on the range that you want to use, okay, the n is still 4 and it is still repetitive. All right, so it means that this is repetitive, okay, or you can choose here, right, as a repeating pattern. That is all right. Okay, so it's any range of n that you can plug into the equations. Okay, as long as it has 4 elements, okay, so it doesn't matter, right? Okay. Anyway, this exponentials, this 2 pi is divided by 4, right? So the value of exponential, no matter what is the k and n, okay, it is you are still repeating using that 4 values from the complex number lah, here, 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 and here lah, okay, to be the value here, right? Okay, so this is something that I would like to inform. Okay, there's a flexibility here, we can change. Okay, so let's say we follow the suggestion by the solution, we use 0 to 3. So we will replace n with 0, 1, 2, 3, and we replace this xn with 0, 1, 2, 3 as well. All right, 1, 2, 3. Okay, and it will be expanded. Okay, there will be 4 terms. Okay, there will be 4 terms, right? 1, 2, 3, and 4 lah. Okay, 1, 2, 3, 4. And x equals 0 equals to 1, right? X equals to 2 is equal to 0, and as well as x bracket 3, right? x2 is 0, x3 is also 0. Okay, so for these 2 terms, actually we do not need to write into the terms. Okay, right? So the last 2 no need to write, because exponential multiply 0 it becomes 0. So what we need to concern is these 2 terms only. Okay, we need to concern x0 equals to 1 and x1 equals to 1, these 2 terms, the first 2 terms, okay, where n equals to 0 and n equals to 1. Okay, so therefore you only see 2 terms here. Okay, so this term is n equals 0. Okay, so if you substitute n equals 0 into here, okay, this you will get 1, right? It's 1. If you substitute 0 into here, okay, exponential power of 0, then you will also get 1. So you end up with a value of 1. Okay, so for the second term, if you substitute n equals to 1 here, add now, you have to add now. Add, this is n equals 0. So this is the result of n equals to 1. Okay, if you substitute n equals to 1, okay, so this become 1. This one can be simplified lah. Okay, so 1 over 2. Okay, so you have 2 here and j pi k at the top here. And for n equals to 1, x1 is 1. Okay, so you have a value of 1 in front of the exponential. So you end up only 2 terms, okay, in these equations. Okay, and this is your ck. Okay, so now that is easy. Okay, you need to find k from 0, 1, 2, 3. Okay, we follow this n equals 0 until to 3. Okay, so depending on the n, so if it says that um, n equals to 4, okay, when it says that n equals to 4, okay, so it means that your n is going to be 0, 1, 2, 3, and your k also the same. All right, if you change your some limit a summation limit for n. Let's say you don't like 0, 1, 2, 3. You say, yeah, I think that doing this is easier. Minus 1, 0, 1, and 2. Then your k would also be must be follow, right? Okay, so you follow the summation limit lah. Okay, right. So that's the case. Okay. Okay, so if you substitute k equals 0, you get this. Okay, if you substitute k equals to 1, okay, so this is k equals to 1. Okay, this is k equals to 2, and this is k equals to 3. Okay, so as you can see, there is a complex number here, right? So they are complex number. Okay, so ck can be a complex number. All right, so that is the solution for C. Okay, all right. So far, any problem? It's no problem. Then we continue. Okay, right, so this one quite straightforward lah. Application of the equations on here. Okay, so this is how we sketch the ck, because here you see the ck, it has a real number, then it has a complex number, it has 0, and then it has another uh, complex number. So when we say please sketch ck, okay, so you can sketch ck versus k lah. Okay, it's all right. Okay, versus k. Okay, for k equals 0, 1, 2, and 3, right? So then you have 0, 1, 2, 3, and you know that the ck is sorry, 0 should be here. Okay, the c is at the origin. Okay. And you know that the ck is periodic, right? So this is 0, 1, 2, 3. So you have a values. Basically, you know the values of C0, C1, C2, C3 lah. Right? And you know ck is periodic. Xn is periodic over n equals to 4. Ck is also the same. Okay, they will be periodic over n equals to 4 also. Okay, so these four values will repeat. Okay, so meaning that C0, C1, C2, C3, you found the value. So if you want to know what is C5, okay, it will be repeating the value of C0. Okay, C6 will take on the value of C1. Okay, if you do not believe, you can change here to from uh, 0, 1, 2. Sorry, this is 3. Okay, this is 4. This is 5. Okay, so if you don't believe, you can try to find from n equals to 4 and 4, 5, 6, 7 until 7. Okay, then you find that uh, the summation from 4 to 7 and the summation from 0 to 3 is the same. Okay, so the C, the Fourier coefficient is repetitive, right? It's periodic. Okay, C2, the value you will find that it will be the same as C6. Okay, so then you can sketch this graph already. Okay, for all the values for positive side and negative side. Okay, so then you get this graph. Right, so this is CK. Let me see. Uh, Spectral periodic signal discussed in example 4.2.1b and C. Okay, so B and C. Right. So it's about this one. Okay, so this is 1 over 2 and 1 over 2 lah. Okay, so this is C minus 1 and C1 lah. And then this is C5 lah. Okay, and this is C minus 5. Okay, so this is the sketches for B. This one. Okay, for B. Yeah. It is all they are all real number lah. Okay, and they are all real number lah. So you only have one graph there lah. Okay, so for the question C, how to sketch it? Okay, so because it is a complex number, so you have to find the magnitude and the phase lah. Okay, versus scale, right? So then you have this graph. So you will see that C0. Let's see. Okay, This one clear first. Okay. For the first one, C0 is a real number. Okay. So for C0, the magnitude is 1/2. Okay. And the angle is 0. Okay. Then if you look at the graph, C0, here is 0, right? So this value is C0, is 1/2. Okay. And the value is 0, right? So the angle of C0 is 0. Okay. So you plot one value here for the amplitude, and the angle you put at the origin. Okay. So how about the next one? And now, so if you look at it, what is the amplitude? Okay, what is the amplitude for this? And you will plot it here. Okay, it is half, and then the angle is minus pi/4, right? So then you plot this for uh, C1. Okay, so this is how you plot it, right? So find the amplitude of C1, and then you also need to find the angle of C1, okay, and then you plot into the graph correspondingly lah. Okay, point by point. So this is a pair, right? It's a complex numbers, right? Okay. So far, this slide is it okay? All right, clear. Hopefully, all right here. Okay. Okay. By the way, anyone is in the campus? No, everyone is at home lah. Okay. All right. So yeah, Kibun said clear. All right, that's good. Okay. Uh, so next slide. So we are talking about the average power lah. Okay, why we are now? So why these terms comes in? Because DTFS is dealing with XM that is periodic, right? Discrete time signal that is periodic. Okay, so when signals are periodic, then it is very natural for us to find average power lah. Okay, instead of finding energy. Okay, uh, when it is periodic, then we look for the average power. So this you have to be always remember. Okay, so for a discrete time periodic signal with period n, okay, the average power can be found by Parseval relation. Okay, so Parseval relation is actually telling us to find the average power. Okay, we can use the Fourier coefficient to find it, or we can use the time domain discrete time signal to look for it. Okay, so there is two ways. Okay, so depending which one is easier lah. To me, both equations are quite straightforward lah, not difficult to use. The complexity is the same. Okay. Here, for example, this when you find the average power, you just need to sum all the Fourier coefficients for n numbers of them. You see here is from n equals 0 until n minus 1. So there are n terms lah, okay, to look for the px. So meaning that you just need to absolute all these complex number ck, square it, just sum them, then that is your uh, average power. Okay, so here this is if you sum this, square this, square this, square this, and square this, and it goes to 4, right? So you just square these four guys here, then you can get the average power. Okay? You get the average power. And so you can also use the xn, okay, the one with 1100, okay, square them, divided by the number of terms, the number of n, then you also can get the average power. Okay, so this is Parseval relation, okay, right? So the average power in the signal is the sum of the powers of the individual frequency components. Individual frequency components means the ck. So each ck representing one frequency, and then it has an amplitude. Okay, so if you remember, uh, we can sketch ck versus k, and this k can be changed to f, right? It is interchangeable. F is the frequency, lah, analog frequency, capital F. Okay, you can change, you can sketch CK versus F if you want. Okay, it's possible. So actually, CK is a frequency spectrum, lah. It's a frequency domain signal. Okay, so how do you change it? This one, we already explained it in this graph before, lah. If you can't remember, then I point it back to you. Is it here, right? So CK versus F, right? So the distance between uh, the CK, right? Obviously, this is C1, C2, C3 lah. So they are separated by a certain F naught. Okay, so where does the F naught come from? It comes from the original equation lah. This time signal dt leh. Let's see. Let me see. Okay, so it's from here. Okay. Uh, if you look at so just now was dt, or when I talk about this topic is actually under Fourier series, continuous time. Okay, but they are using the same CK lah. So actually there is a relationship. Okay, if you look at this CK equation right? So EJ 2 pi kn divided by n, right? So you found that there is a k versus k over n here, right? So actually this equation can be written as 2 pi fn, okay? And here is omega, right? Omega equals to 2 pi f, right? And then you can also write this as a exponential j omega n, all right? Omega here can be also expressed as uh, how to say omega t. Okay, uh, this t is the sampling frequency, right? So it's a sampling frequency, sampling period. Okay, and here there's capital F lah. All right, so here can relate to capital F lah. So this is the sampling frequency, sampling period lah. So where do you get this? I think in previous chapter that we have seen before, right? This can be derived lah. Uh, it is from this F, how to say, uh, uh, small letter f equals to f divided by fs, right? So if you multiply 2 pi here, and also multiply 2 pi here, okay, you found that this can be written as omega, this can be written as capital omega, all right? And this one, 1 over fs can be written as t, okay, ts lah, right? So then you will get this. So it somehow come back to, it can be translated, you can translate from k, okay, from this k to this f lah, right? So in this case, maybe later on when we go further, then we will see what is the relation between these two lah. Okay, so it actually can be uh, translated. Just that the distance between the lines is fs, okay, the sampling frequency, okay, because xn is we got xn from x t lah, right? Then to change from a continuous time signal to a discrete time signal, we need to sample it, okay? So that sample it, after you sample it into xn, okay, and you convert it to ck, and you eventually will found that, oh, the line between uh, the ck, if I change it to f lah, I don't want to use k equals to 0, 1, 2, 3 as the x-axis. If I wanted to use f-axis, then you'll find that the distance between the ck is actually the sampling frequency, right? Okay, right. So you can check, okay, you can check that one, right? Later on, from maybe from other sources lah. But the textbook also not mentioning this very clear. Okay, but if you check other sources, then you would found that actually this distance is fs. Then actually I can use capital F as my x-axis. Okay, right. So therefore it says that individual frequency components. Actually, this line, this x-axis here is representing the frequency axis lah. Okay, that's why it says like this. Okay, all right. Okay, so to understand that, you need to do some homework. Okay, to get yourself familiar. What is this graph? Okay, CK versus K. Okay, and so on. And sometimes in the textbook, in the online resources, you found that people actually plotting versus F, right? Okay, so then you should know um, what is the rationale people want to use F, right? Okay, okay. So that's the message that brought by this sentence. Okay, the sequence CK absolute square is the distribution of power, right? So average power, okay, and it is called the power density spectrum. Okay, so if you square this graph, every one square, right, then that's the power density spectrum. If we are interested in the energy of the sequence xn over a single period, okay, so meaning that let's say we don't want to find the power, okay, now we got the power of the uh, signal of xn lah. Okay, the signal of xn. Let's say we want to find the energy over only one period. Okay, so we limit the summation from n equals 0 until n equals to minus 1. Because if you look at the equations for energy, it is the summation is from n equals to minus infinity to infinity. Okay, so if we only want to look at one sections of the period, and I wanted to know the energy within this period, okay, so we just limit it from 0 until n minus 1 lah. Okay, so we don't go from minus infinity to infinity lah, because if you do this on a periodic signal, the energy is going to be infinity, correct? Because periodic signal never ends ma. Okay, so we just limit the summation limit here over a single period, which is n equals to 4. Okay, and then find what is the xn squared, right? So then we'll get the energy over one single period within that period only. Okay, and can we use, instead of xn, can we use ck? Yes, you can also use ck to find the energy over one single period. Okay, but you need to multiply with n. Okay, right? So this is more or less you can look at it. It's just push this n over here, right? If both are equal, right? Just put this over here. Okay, then you get, this is the energy in one single period lah. Okay, as here lah. Right. So so this something that we notice over here lah. Okay. Right. Uh, so another example. Okay. Determine the Fourier series coefficient. Okay. So meaning that look for CK. All right. And the power density spectrum. Okay. So meaning that look for CK absolute square, right, of the periodic square wave signal. Okay. So just now we were, now this is actually it's a square wave, right? Why it is a square wave? Because it looks like this, right? Okay, if we connect the line, then it looks like a square wave, right? Maybe like this, right? So a square wave. Okay. Now we wanted to find the CK and CK absolute square for this square wave signal, where the amplitude of the square wave is A. Okay, so this is xn versus n, right? Or xn versus t. This is a time domain signal. Okay, so this is A, discrete time signal with amplitude of A, and the number of element with a value of a is from 0 until L minus 1. So there's L element. Okay, so if you look at here, it started from 0 and it stopped at L minus 1. Okay, so the number of element with a value amplitude of A is L. There are L of them. Okay, then there's some 0 here. Okay, so the 0 is stopped at N minus 1. Okay, all right, so including the 0, so we will say that the whole uh, the total um, element within this one period is n, right? Including the one that in 0 now, but the one with value is 0 until L minus 1, and then uh, the number of 0 is here. Okay, the total element with amplitude a and also 0, there are n of them. Okay, so this is what we understand from this graph. And the value of L and N is not given, so we are forced to use N and L as the variable in the equations to solve for CK lah. Okay, so that is the case here. Right, so CK, so what is the equation we are going to use? Okay, uh, the answers, because we are looking for CK, the solution suggests us to use the second equations. This one, okay, find the CK given xn, right? Okay, so it is good that there are some 0 in the xn. Okay, so we do not need to sum from n equals 0 until n minus 1 because here is 0. Summation of 0 is just 0 now. So we will change the limit from n equals 0 until L minus 1. We just need to sum this range of uh, terms only. Okay, exactly how many of them we don't know because we are not told what is the value of L. Okay, we just have to replace it with L minus 1. We will do the summation from n equals 0 until L minus 1. And the amplitude in this range is A. Okay, so the xn is A in this range. So we replace this xn with A. Okay, and we don't know. Okay, so we leave it as n. Okay, this one you also don't know. Okay, so we leave it as it is lah. Okay, so we uh, start off with these equations, right? Then we do these equations, right? Okay, so how do we do next? Okay, so let's um, factor out the n. Okay, so we rewrite the equations uh, n that is factored out. Okay, if you multiply in, it's still the same now for the exponential now. Okay, and then this a will move it outside and put it here. Right, move it outside since it is just a constant over the summation. So we can take it out. Okay, all right. So this one we clear. Um, okay, so then after that, then we will replace the n from 0 until L minus 1. Okay, for here. Okay, so if n equals 0, let me see. N equals to 0. Let me see. Something is missing. See. Okay, yeah. Right. So if n equals 0, right? Because now if you want to expand the summations, what we are getting ck equals to a divided by n. Okay. And then the first term should be n equals 0. Okay. If n equals 0, then it would be 1, right? Because if it's 0, then multiply in, then exponential minus j 0, then it would be 1. Okay. Let me see. Is it true? Okay. Then if it is 1, then you have exponential minus j 2 pi k n 1. This is n equals 0 lah. Then this is n equals to 1. And then this is n equals to 2 and so on now. So when do we stop? Then we will stop at this 2 plus until we will stop at L minus 1, right? So we will stop at E minus J 2 pi K divided by N L minus 1. Okay, then we'll stop at here. Okay, right. So if now we have expanded the N, all right? So the N is iterated. Next is want to iterate the K lah. So if K equals 0, so all this K goes to 0, right? All this K goes to 0. Okay, so there will be 1 plus 1 plus 1 plus until 1 here, all right? So there will be uh, L values of 1. If you add all the 1 together, then you will get A L over N. Okay, so all these term 1 plus 1 plus 1, if you sum them all, you will get L. Okay, because there is L term. Because you have N equals 0 until L minus 1. Supposedly you have L number of terms inside this bracket. Okay, so if every element in this bracket has a value of 1, okay, then if you sum them up, then you get L. Okay, so therefore you have L here. Okay, right. So therefore this is the first term for K equals 0. Okay, all right. So if you understand that, then let's look at how do we get the second term. All right. Okay. So the second term for K starting from 1, 2 until N minus 1. Okay. Uh, why it is ended up in N minus 1? Remember that I said that um, for these equations, right? So Xn actually there are n terms, right? Supposedly it should go from z until n minus 1. Okay. So the n this small letter n must be iterated from 0, 1, 2, 3 until n minus 1. We are simplifying it until L minus 1 because we know the 0, uh, we don't need to calculate for the summation of 0 lah. Okay, but according to equations, the n must be iterated from 0 until n, capital N minus 1, and the k also, right, until L minus 1 actually. Okay, until n minus 1. Okay, so these two must follow. Okay, uh, so but for the calculations for this summation, we stop at L minus 1 because this one no need to calculate. Okay, but it doesn't mean that our k also iterated from 0 until L minus 1. It has to be go beyond until N minus 1, right? So, okay, so it stopped at N minus 1. So the equations is this, right? So how do we write this equation out? From a summation of a range of exponential. Okay, because you see, I if I want to find C1, right? So meaning that all the k has to be replaced with value of 1. Okay. Okay, so I have e minus j 2 pi over n. I don't know what is the value. Okay. But the k can be replaced with 1. So 1 minus 1. Here is 1 minus 2. Here is for this term is 1 multiply L minus 1. Okay. But the exponential is there and cannot be eliminated, and it exists. Okay. But it is if you look at the pattern, it is uh, geometric summations. Okay. If you look at here, right? So if you have a summations from 0 until n minus 1 for a that is power of n, then you can simplify it into this term. Okay, if the a is not equals to 1. Okay, so what does that mean? So it means um it means oh, okay, it means for this term, right, I need that a lot of exponential, but let me explain this to you. Okay, so if you expand this summation, what does that mean? So it means it means uh, n minus 1, n equals 0, a to the power of n is actually a power of 0 plus a to the power of 1 plus a to the power of 2 plus a to the power of 3, and so on until a to the power of n minus 1. Okay. All these summations, it can be written into 1 minus a power of n versus divided by 1 minus a. Okay. Under the condition that the a is not equals to 1. Okay. So in this case, the capital A here, the small letter a here is actually exponential minus j 2 pi k divided by n. Okay. So they are this. This is your a. Okay. So this is your a. Right. So you can apply these equations, okay, to become this lah. Okay. It is summation from 0 until L minus 1. Okay, so this is a to the power of n, and here you can write it a to the power of L. Okay, right. So because it stopped at L, right? So you have a to the power of L, okay, and then the rest follows. Okay. So why we are saying that this is not one. This obviously this is a complex number, and it cannot be one because if it's one, then it will become infinity. Like you cannot plug into this equation here. Therefore, it says that it cannot be one. Okay. If it is one, then you just use this as the solution. All right. So in this case, we can rewrite these equations, okay, this sort of summations, okay, into this. All right. Okay. So based on this geometric summation formula, lah. Okay. All right. And then there is a further things that we can do. Uh, so when we have this, right, we want to do some multiplication on this 1 minus exponential divided by 1 minus exponentials. Okay. First of all, okay, let's factor out. Okay, we will factor out the e minus j pi kl over n. All right. What is the reason that we wanted to factor out from here? We want to factor out e minus j pi kl over n. Okay, we want to factor out this term lah. Okay, so this is the bracket. So we want to factor out this one. But if you multiply into this bracket, you will get back the same term as this lah. Okay, but we want to extract e minus j pi kl over n from here and here. Okay, right. So the reason we wanted to do this because we want to create the terms of exponential positive j and another exponential minus j. Right, you want to create this term lah, one positive j, one negative j, so that we can write a sign. We can write a sign term here lah. Okay, so that's the reason that we want to do. Okay, this is the solution from the textbook lah. So I found that this is the intention now. Okay, so you factor out this term for the top. At the bottom, you factor out this term. Right, so this is the bracket. Okay, you factor out. All right, so the top terms you can write into sine. The bottom part you also can write it into sine. Okay, then you get this and this. Okay, right, and for these two terms, you can do a subtraction for the power. Okay, you can do a subtraction for the power. Okay, it's L minus 1. Okay, right. So why do we want to do this? Because if you plot it out, it looks like this. It's a sinc function. Okay, this is the graph. It looks like a sinc function. Okay. Uh, you see, this is L equals to 2, N equals to 10, meaning that in Xn, it looks like this. L equals to 2, right? So 2, and then 8, 0. 1, 2, 3, 4, 5, 6, and 0. Okay, so this is N, right? So it looks like this. For this, it is L equals to 2, and then N equals to 40, then you have 38, 40, 0 here. So it's 38, 38 zeros. Okay, then you got this graph. If you plot it using this equation, okay, I plot it using this equation, right? Okay, meaning that here now, plus the CK versus K lah, right? Okay, so this one gives us somehow a sinc function, right? Looks like a sinc function, but periodic sinc function lah. Okay, periodic sinc function. If you look at this, right, and this, right, so like this. Then after that it repeats, then repeats, right? Okay, okay, right. So so uh so therefore then they simplified it into this term. Okay, they simplify into this term. Okay, so this is your CK, your the answer that you're looking for. Okay, real coefficients. Okay, the expression without value. Okay, because they are not giving us value also, so we express them in L and N also lah. Okay, and then the power density spectrum, just square them, absolute and square it. Okay, so you see that the answer here is square. Okay, and this one also square, right? And you see that this complex number, when you find the absolute, it's not there anymore, right? Because this is a complex number. So Ej theta is a complex number. But if you find the absolute of this complex number, then it is one, right? So it's just one here. So for the spectrum density spectrum, this one can directly take away. Okay, you just need to care about the sign terms and also the AL over N here, right? Okay. Okay, let me see. Uh, there's an L here. Is it a mistake? This one. I think this is a mistake. Shouldn't be an L. Yeah, this shouldn't be an L. I think this is a mistake. Yeah, please take note. I'll verify again in the textbook. Somehow this one. Okay, I'll verify it again in the textbook and I'll update you again. This one should be an L or not. Because when I look at it, there's no summations. Uh, there's no summation terms lah, so I don't see why there's an L here lah. Right. Okay, so maybe that's the mistake here. I will temporarily take it out first. Yeah. And I believe this is the answer. If I square this CK lah. Okay. Um, I'll update you again on this. Right. Okay. Anyway. Yeah. Right. So we found the CK and also CK absolute square, right? And if you plot the graph, then we see this. Okay. Why is that the resolution, if you can see, the frequency or the cycle per sampling interval. All right. So the interval between here is actually the uh, sampling interval lah. It's a sampling interval. Okay. Um, why is that the Sn that has L equals to 2 and N equals to 10 would have a very poor resolution. Okay, but if you have an n equals to 40, okay, then you have a much better resolutions in the frequency domain. Okay, so here there are 38 0, right? So here is 8 zeros, right? So obviously this graph is much more uh, the resolution of the frequency is better. Okay. The difference between these two graphs is that the second graph has 30 more zeros. Okay. Appended. Okay. Appends to these two guys here. Okay. So these are the zeros that following them. Okay. So you see that the resolution is much better. Okay. In terms of the frequency axis lah. Okay. Why is that so? Okay. Because essentially, um, oh, actually, we learned this before. It's very related to what we see here with these slides. Okay. So there's a one sentence here saying that if we allow the period to increase without limit, okay, period means the t lah, okay, the line spacing tends towards zero, then they will all merge together. Okay, the line spacing tends towards zero, meaning that this is a Fourier series, continuous time Fourier series, CK lah, but it is as I said, uh, it has an analogy with our DTFS also. Okay, so the if you have the t that you keep increasing it, okay, so the line spacing is become closer and closer. Eventually, they will merge together, right? So here also the same. Okay? If you if you have the these 2 point, right? If let's say you are pushing the neighbors, so after 8 0, there's another neighbors here. DTFS ma, so it should be repetitive every n equals to 10, right? So if this neighbor you are pushing it further and further away, then uh, the line is will be more packed. The line spacing will merge together. Okay. So this for this case, for the second graph, this another group of n equals to 40 is so far away. Okay, so the neighbors are so far away. Okay, so you will have more resolutions in this CK graph. Okay, so in other words, in other words, let's say you wanted to increase the resolution from here to here, right? Okay, you can pad with zero. You can pad them with zeros. So this one 8 0. If you pad more zero, you put another 30 zeros. Then the resolution will become better. Padding zeros also means that if you increase, okay, the sampling interval, decrease the sampling interval, right? So let's say this period, they are n equals to 10, right? So you sample 10 points, okay, from these periods. If you sample um, 40 points from this period, okay, then your resolution, of course, become better, right? So this is another way to understand how to increase the resolution of the spectrum lah. Okay, so the more you sample, you can increase the uh, resolution of the graph, or you pad more zero. Okay, you pad more zero also can increase uh, the spectrum of the graph lah. Okay, from here to here. In fact, if you look at the values here, right? Okay, so if you overlap them, actually they are overlap to each other, the values. Okay, so it is 5 here, right? So the next one here is 3, then at the point of 3 you also see the same values. All right, so that is something that we notice from this DTFS CK graph. Okay, right, so this graph actually telling us how do we make the resolution of the spectrum better. Okay, we can pad with zero, or we sample more during this period. Okay, the the idea is that we have a better end. So we have a better end. The more end, the better. Okay, the more end, the better. So this is the essence of or these slides are. Huh? Okay, so I hope everybody got it. Okay. Okay. Uh, since this is recorded, I will continue to explain DTFT. Okay. For the next 45 minutes lah. Okay. Let me see how many slides we got here. Oh, okay. Then properties already finished. Okay. And I think we can finish off this chapter 2.1 already. Okay. Okay, DTFT. Swap. Okay. Right. Okay. Right. So just now the previous slides just give you a quick um, overview again. We started off with CTFS, okay, continuous time Fourier series, okay, and we are talking about CK, right? Then we talk about CTFT, and that time we talk about X, capital X and F, right? This is the Fourier coefficients, okay. Uh, Originally it was XT, okay, and originally this was XT, okay. Then they can be transformed into CK or transformed into XF, depending on whether they are periodic or not periodic. If XT is periodic, we can transform it to CK. If XT is not periodic, we can transform it to XF. Then we also learn about DTFS just now, right? And it can be transformed to CK also, right? So they share the same notation as CTFS. Okay. If it is periodic. If Xn is not periodic, okay, then we should use DTFT to transform it into X small letter f, and sometimes capital X small letter omega, right? Uh, so this two is interchangeable. I forgot to write here. We can also use capital omega for the transformations of CTFT. Okay, right? Small letter f and small letter omega, their relationship is 2 pi f only. It's a constant multiplication away. Okay, so essentially they are the same lah. So you can write your capital XF or capital X omega, okay, using either of these two variables. Okay, so now we are here. Okay, we are in the final part of understanding DTFT. Okay, after we done this DTFS and DTFT, if we already understand, then we should move to uh, understanding FFT already lah. Okay, right. Okay, right. So for DTFT, discrete time a periodic signal, meaning that the xn is not periodic, right? It's not periodic. Type to my okay. Okay, so um, so we are so the transforming pair is xn and also x omega lah. Okay, small letter omega, and you will see that here is an integrations. Okay, it's an integrations over 2 pi. Okay, why 2 pi? Because we are integrating over d omega. Okay, so what is omega? Omega is the normalized frequency that is in between minus pi to pi. Okay, so we will integrate over this range only. Okay, the fundamental range. Okay, right. So let's say, meaning that if you have x omega, okay, that is defined between minus pi to pi lah. Okay, maybe it is something here, right? You just need to integrate this negative over this period only, because the next 2 pi is a duplicate of this, right? So this uh, x omega, they will, according to the properties of discrete time signal, okay, it is no the it is repetitive over every 2 pi, right? So we only need to integrate within this fundamental period only, okay? So therefore you see there's a integrate over 2 pi here, okay? And then you see that it is an integration. It means that this x omega is a continuous variable. What happened to my pen? Okay, so it is a continuous variable. Okay, therefore it use integration. All right, and uh, here it is a summation term because xn is a discrete time signal. Okay, and interesting enough, okay, they are using ej omega here and minus ej omega here, right? Where the omega is 2 pi f, right? So this is the equations that we need to use for DTFT. Okay, right. So this xn is not periodic, right? It's not periodic. Therefore, you see that the n, it is summation. It is we have to sum it from minus infinity into positive infinity, right? Because there's no n, there's no capital N fundamental period there, because simply the xn here is not periodic, right? So there's no value of this. Therefore, no choice. Okay, so uh, we have to sum all the xn, right? So that is uh, this is the situation here. Okay, so the differences between the Fourier transforms of the discrete time and continuous time signal is that, so they are now comparing DTFT and the CTFT lah, right? Okay, not sure why my pen is like that. So the frequency of DTFT is from minus pi to pi. Okay, so this is the DTFT. The frequency is from minus pi to pi. Okay, while for CTFT, it is from minus infinity to infinity. They are talking about this capital F, right? It is from minus infinity to infinity, right? X omega is periodic with a period of 2 pi, okay? Meaning that x omega plus 2k pi will be having the same value, all right? So we know that in the chapter 1 already, this is the fundamental frequency range, yeah? So the next 2 pi, if there is a x omega defining within this range, so the next 2 pi, this one will repeat, okay? So they are uh, periodic. So S omega is periodic. This is the keywords, right? S omega is periodic, right? Okay. uh, okay, so next, energy density spectrum of DT, okay, aperiodic signals, right? Yeah, so we are talking about energy instead of power, okay? Simply because the signal now xn is aperiodic signal, okay? So when we deal with aperiodic signal, then we look for the energy density, the energy signal, okay? So the energy, according to Parseval relation again, the energy can be found from the discrete time signal xn, okay? Of course, the summation is from minus infinity to infinity, absolute square now. Or you can look for the energy through the Fourier coefficients x omega, okay? But you need to, because it is a periodic signal, okay, so you need to integrate it over 2 pi lah, okay, and divide it by 2 pi over the omega range. Okay, both way can help you to get what is the energy of the signal. Okay, and if you are plotting x omega versus omega, okay, absolute square versus omega, then you are plotting the energy density spectrum. Okay, and every for your information, this x omega, okay, can be a complex number. Yeah, it's a complex number lah. Okay, so you absolute it and square it, then they will be all uh, in the positive side of the graph lah, upper part. Okay, all right, all right. Okay, if you have any questions, you can stop me and ask lah. If not, then I will just continue. Okay, for this example, it is a bit interesting. Okay, find the inverse DTFT. Okay, right, find the inverse DTFT, meaning that when you see this, meaning that they give you x omega, please find what is xn. Okay, if it is forward DTFT, then they give you xn, find what is x omega, which is most of the time the case lah. But sometimes we need to, sometimes the question will also ask, uh, find the inverse, right? So x omega is given. Okay, it is 1 for the omega within omega c. Okay, and it is 0 for the omega between omega c and pi. Okay, so if we sketch the signal, it looks like this. Okay, with a value of 1, right? So this is 1. So here is minus omega c, here is positive omega c. Okay, so I hope you can understand this writing lah. Okay, no matter it is positive or negative, it must be smaller than omega c. Okay, so which is this region. Okay, from omega c to pi is all 0. Okay, so this is the x omega versus omega. All right, so I'm sketching from minus pi to pi lah. Of course, if you want to sketch from uh, if you want to sketch the other region, then there's another one here and there's another one here. Because x omega is uh, periodic over 2 pi. All right, so the next 2 pi, you will see x omega again, whether it is right side or left side lah, following this statement here lah. Right, okay. So this one we must understand lah. So there is aliases, okay, in the left and right according to the theory, right? Okay. All right, so now we wanted to look for the okay, I no need to wipe it off. Okay, so I want to look for the xn, and we decided to use this equation. Okay, so if you wanted to integrate x omega, right? So we'll do it now. So let me write the equations here. So xn equals to integration of 2 pi. Let me see. Does it have a one multiplier of 1 over 3? Yeah, right. I have to multiply 1 over 2 pi in front. So better write it off. Okay. So I need to multiply it with 1 over 2 pi here. I write down the initial equation. Does it have a negative or no? No negative, right? Just j omega n, d omega. All right. Okay, so I wanted to integrate x omega over 2 pi. Okay. In fact, what is going to happen is that I will integrate from minus pi to pi. Okay. Looking at this graph, right? So the range is from minus pi to pi. Okay, but I found that between minus pi to omega c is 0. So I do not need to integrate the 0 part of the graph lah. So I can integrate from minus omega c to positive omega c. All right. So therefore, And in between this range from minus omega c to omega c, the value is 1. The x omega value is 1 in that range. Okay, so this is what I noticed. So instead of minus pi to pi, I change it to omega c to minus omega c to positive omega c. And the x omega, I change it to 1. Okay, so there's a 1 here. Right, so I end up with these equations. Okay, with this equation, right? So it is from minus omega c to omega c, and there's the 1. So this s omega, I take it away. So essentially, I am integrating exponential, right? Then if I integrate exponential, then I have uh, uh, jn go to the bottom, right? Okay, and then I will need to replace this omega c and this minus omega c into this omega. Okay, because I am integrating with respect to omega, right? So I need to replace the variable omega with the limit. Okay, then I found that uh, I would have, if I replace the omega with positive omega c and negative omega c, I would end up ej positive minus ej negative like that lah. Okay, so this sort of uh, two exponential with a negative sign. So this is actually, we can relate it to sine theta equals to 1 over j2 ej theta minus e minus j theta. So it is actually giving us a sine term. Okay? It is actually giving us a sine term. Do we have j over 2? Yes. We saw that there's a 2 here and there's a j here. Okay, so we can use these 2 and j together with the positive and negative exponential to write the sine term. Okay, then you see that there's a sine term here. Okay, right. So the detail how to get that, okay, you simply you can do it yourself, right? So you got the sine term here, and then you have um, an extra pi n, okay, that come from here. Okay, and you see that this is actually a sinc functions again. All right, so in fact, a square wave of x omega will give you an xn that is a sinc functions, right? Okay, right. So but when you got this, okay, the problem is that the equation doesn't allow you to use n equals 0, because xn, of course, it will, the n is go from minus infinity to infinity, for n equals 0, n equals to 1, and all the integer lah. But for these particular questions, for these particular equations, n cannot be 0, because if you put n equals 0 here, then xn is infinity, which is not correct lah. So so we need to find another way to get what is my x0, right? So for n equals 0, okay, before you do the integration, right, you substitute x equals 0 first, right? So the n equals 0, this n equals 0, then only you start to do the integration, right? Okay, so x0, this one, make it to 0. Then in between omega c and minus omega c, the value is 1. E j omega 0 is already gone, is 1. Okay, so you are integrating 1. Okay, you are integrating only a value of 1. Then you get omega c over pi lah. Okay, so the final solution is that your xn is omega c over pi at n equals 0, and the rest is sine over pi n for n not equal to 0. So if you plot this xn versus n, okay, for n equals 0, you will use the value of omega c over pi. Okay, omega c is uh, the value here lah. This is x omega, right? So this is the omega c, this is minus omega c, right? Use this. put it here. And the rest of the values here or here, you will use this sine omega Cn divided by pi n, right? So the value after beside n equals 0, then you use this equation to sketch it, right? So this is how it looks like, all right? So this is xn over n, okay? So at the origin, you use omega c over pi, and the rest of it, you use the sine omega c uh, n, right? Omega cn, yeah, omega cn versus divided by uh, pi n, right? Then this is a sinc functions. If you look at it, right, then you will see that there is a zero crossing at pi over omega c. The next one is 2 pi omega c and so on, right? There's a zero crossing. Okay, so this is your s omega versus omega lah, all right? So the square wave, if you inverse Fourier transforms, then you get a sinc function. Okay, all right. And if you look at the equations here, it is saying that n not equal to 0. Okay, and you use these equations. It also implies that uh, this xn uh, values, it never ends, right? So it goes towards the infinity. So as long as n not equal to 0, you should continue plotting it. All right. So actually, this is a infinite sequence. Xn is infinitely long, right? So the equation, actually, this is saying that xn is a infinite sequence. It's an infinite sequence, right? It's uh, it never ends lah. Okay, because we know that the sinc functions uh, it will continue to oscillate towards the left and right, but it never uh, becoming zero lah. Okay, right. So this is the situation lah. So the theory also in telling us that the interchangeable between these two, the theory says, if you have xn that is infinite, if you are able to collect all the all the values in xn, which is an infinite sequence, you can construct a perfect square. Okay, you can construct a perfect square wave in the frequency domain. Okay, if you have not enough, if you cut it off here, you only have 50 values from xn, then you might not be able to get a perfect square in x omega, right? So that's what it means lah. So the theory says if you want to have a perfect square, all the values in xn has to be in, according to the mathematics, okay? Which is not practical in engineering sense now. So how can an engineer build a memory to store infinite values of samples from xn, which is not possible. Yeah, so we can only approximate in this case lah. Okay, all right. Okay, consider we would like to have this xn. Okay, uh, for the consider the, I think the sentence got problem. Consider the finite summation. Okay, so meaning that if you look at the equations of DTFT, right? This equation actually come from here, right? To construct x omega, you must sum all the possible xn from minus infinity to infinity. Okay, so it's good. Okay. And now our memory, that memory chip or memory size that the engineer fabricate is not able to house all the possible value of xn. Okay, so it can only uh, store up to 2n values. Okay, so what happened to the x omega if we truncate lah? So we cannot store infinity lah. We only store up to 1 million, minus 1 million to positive 1 million lah. Okay, so what are we getting? The result is that if we do that, if our n is not sufficient, for example, n equals to 1, n equals to 3, n equals to 7, 15, 50, and 70, you can see that this is the ideal case. Okay, so this is your x omega that you calculated using a limited summation, finite summation of n. Okay, so as the n increase, you will see that it approach better to the to the ideal square wave. All right, if we further increase the n, it looks better, approach better, right? And until you got up to 70, then it is very, very good fit already. Okay, but it is still not a square wave to be exact, right? To be strictly speaking, it is still not a square wave, but it is very, very near already. Okay, it looks very fit already. Just that it has some oscillations here. All right, here's some oscillations that we cannot avoid. Okay, right. So some oscillation that we cannot avoid, but as the n increases, the oscillations also will merge. The oscillation is becoming very furious, but they also pack with each other, lah, right? So and we understand that if we increase this to 700 million also, okay, we still have this spike lah, this oscillation lah, okay, or the overshoots, right? The oscillatory overshoots, okay, which is independent of the value of n. Okay, meaning that if you have n equal to 70 or n equal to 70 million, the overshoot is still there. Okay. As the n increase, the oscillation becomes more rapid. Okay, of course, you see, this one is less rapid. N increase, it become very packed and very rapid. But the size of the ripple remain the same. Okay, so the size of the ripples, okay, the amplitude of the ripples is almost the same. Okay, it doesn't reduce. Okay, if n goes towards infinity, the oscillations converge to the point of discontinuity as omega equals to omega c, but the amplitude does not go to zero. Okay, uh, if you um, let me see. So it says that if n approaching infinity, the oscillation converge. Okay, so meaning that there's no more oscillations. But the amplitude does not go to zero, so the amplitude will remain this. The equation says that. Okay, so this oscillatory behavior is known as Gibbs phenomenon. Right? Okay, performing DTFT with truncated series. Okay, so the Gibbs phenomenon is the result of uh, truncated DTFT. Okay, so we should know that in our real life engineering designer, okay, Gibbs phenomenon, when we design filters, low pass filter like X omega, we cannot really get rid of this Gibbs phenomenon. We can only reduce it at as much as possible using other methods, other techniques. Okay, right. So this is something that you need to look into uh, in in the preparations of your lab sheets now, lab report. Okay, right. So okay, so this is the case. Okay, the more n, the better, obviously. Okay, but there is some things that we uh, have to take care of. Okay, cannot be avoided. Okay, which is the Gibbs phenomenon. Right. Okay. Right. So the summary. Okay. Continuous time signal. Okay, we call it CT lah. Have an aperiodic spectra. Okay. So continuous time signals meaning XT. Okay. Their spectra is aperiodic. Okay. The XT, if you convert it either with DTFS or DTFT. Okay. If you DTFS, then you got CK. if you convert through DTFT, continuous, right? So it should be CTFS. Okay, okay. CTFS, CTFT. This one you get X capital F lah. Okay. Uh, these two, this CK and XF is not periodic. All right. So we have an aperiodic spectra. So this is what it says lah. Okay. And then the second one, discrete time signal have a periodic spectra. Okay. So XN, whether you convert it through DTFS or uh, DTFT, okay, you will be getting CK also. And here you got X omega or XF lah, small letter F, right? So this one I should write X omega, okay? And they are periodic, okay? So these two are periodic spectrum, okay? So this is what the question says lah. So these are some explanation um, uh, that you can read through lah. The equations actually uh, tell us that they would be periodic now, okay? Right. Then periodic signal have discrete spectra. Okay, so if the signal is periodic, so it will go through CTFS and DTFS, right? Right, whether it is XT or XN. Okay, so the spectra is discrete. Okay, so it will be CK. You will get CK, and the CK is a discrete variable, right? It's a discrete variable. Right, so this is the summary of this equation of the CTFS, CTFT, DTFS, DTFT. Aperiodic finite energy signal. Okay, it means that energy signal means aperiodic lah. Okay, you will get continuous spectra. Okay, if the signal XN or XT they are not periodic, then you'll be getting a continuous spectra, meaning that um, your this XF or X omega or small letter X omega and XF, they are the continuous variable. As you can see from the equation also, uh, you are using integrations on this variable, right? So they are continuous spectra, okay? So these are the summary characteristics that we uh, learned about lah, okay? Right. Finally, okay, so this is the table, okay, to summarize what we have learned, okay? Right, so how to interpret this table? Let's look at the first quarter, okay? It's a periodic signal, and it is a continuous time signal, right? CT uh, is periodic, right? It's periodic, meaning that it has T lah, okay, as a period, okay? So this is XAT versus T. Then the CK versus F can be plotted through this equation, okay? So this is the CTFS equation, FS here, right? FS. So it is a CTFS equation, okay? So this is a sample lah, okay, from continuous variable to discrete variable, right? Okay, continuous and periodic. Okay, it is talking about this XAT. Discrete and aperiodic is talking about this CK lah. So next one is aperiodic signal. Okay, but it is still under continuous time lah. Okay, so XAT, it is not periodic, and your XF is also aperiodic, right? Okay, so this is the so-called the CTFT equation, right? So this is CTFT. Okay, now we look at discrete time signal. Okay, so Xn is periodic. Okay, then you will get your CK. It is just discrete variable and also periodic, right? So periodic. So CK is periodic, right? if your Sn is not periodic, by the way, the equation here is DTFS. Okay, right. So if your signal Xn is aperiodic, then you would use DTFT to find your X omega, which is a continuous variable, and they are periodic over 2 pi. Okay, they are periodic over 2 pi. And this is the equations that uh, define the DTFT. Okay, so in short, you have the equations of CTFS, then you have CTFT. This is how it looks like. And you have DGFS and DGFT. Okay, so these 4 columns summarize um, the whole things that we learned, okay, including the equations also given here, right? Okay, right. Okay. Let's us quickly go through the Fourier transform theorem and the properties, okay. So they are linear. Fourier transforms is linear. Okay. Uh, so if you notice here, this is actually DTFT, okay, right? So x1, uh, if x1n, because in general x1n is we can say um, actually DTFT or DTFS, they actually share the same properties now, but uh, the textbook use DTFT as the example. So x1n, uh, if you do the Fourier transforms, you get x1 omega, and then you have another sequence, x2n, you do Fourier transform, you get x2 omega. You can uh, combine these two and multiply them with a constant, okay? And you can get the aggregate Fourier transforms by using back the value here. Okay, you can use back it. If you know the individual transforms answer, then let's say the question asks you, okay, I want to combine all this time domain signal, scale it with A1 and A2. Please find the overall Fourier coefficients. Then you can use back the individual x1 omega and x2 omega, plug it in, then you can get the overall x omega also, right? So they are linearity. Okay, there's a linearity properties there, just like what we learned in LTI lah. Okay, so for time shifting, okay, so let's say you know what is the answer for Sn and x omega. You already know what is the DTFT. You know it, okay? Uh, let's say now the question say, okay, I want to delay this by a number of k, by k unit of time. And what would be my x omega? Then you can use the same x omega, put it back here, but you multiply it with an exponential, and the k is replacing here. Okay, then you got the answer, right? So this is the time shifting properties. Okay, so it always started off with, do you know what is the DTFT of this Xn? Then if there is any changes of this Xn, you can use back this value, right? You can use it back, right? Right. So it started off with uh, do you know the pair lah, right? Okay, right. Okay, so same thing, time reversal. If you already know this, you know the answer of x omega. Now the question says, okay, let's inverse this. Okay, then you are on the, for the s omega, you also fold it, you fold it around the 0 point. Okay, same thing, time reversal. Okay, about convolution. Okay, if you know x1 give you x1 omega, x2n give you x2 omega. If I now do the convolution of x1 and x2, okay, what is my overall uh, Fourier coefficients? It will be multiply. Okay, you just need to multiply these two together to get the answer. Okay, so meaning that in time domain, the operations of convolution is corresponding to the multiplication in frequency domain. Okay, so this is multiply. Here we do convolution. Okay, all right. So in that case, we will see that multiplication is easier. So people would prefer to convert x1n to DTFT first, then only do multiplication to get the answer lah. Okay, because convolution sometimes is very difficult to do, right? Okay, correlations. Okay, so this one is not related to RMH lah. Okay, so if you have you know what is x1n and x2n. Okay, if you want to do correlations between x1 and x2, okay, then you also go through multiplication, but one of the uh, x2 omega, okay, must be folded. Okay, either one, right? So so the multiplication of these two is called the cross energy density spectrum. Okay, all right. All right, so that is the properties of Fourier transforms. Okay, then we can stop right here for today. I will post the recording later on into the Google Classroom after this class lah. Okay. Right. So far, do you have any questions to ask? If everything is okay, if you miss any parts lah, or you do not understand any parts, please look back the video recording. If not, then you can also ask me in the class lah. Or I can anytime you can post the question to me and we discuss together with the class. Okay, thank you for your time on Saturday to be with me here. Next week, Saturday, we will also see you again, okay, for the replacement. Thank you, everyone. Right. See you next week.